Buenos días, bienvenidos de nuevo al tercer y último día del...
Well, this is our third day of our Congress, DRT for All 2009. In previous editions of this Congress, we've always had some time devoted to science. There's also time for live demonstrations. We will also have time for users, as usual. This will be after breakfast. And on the last day, we devote time to live demonstrations which are linked with the scientific issues which have been covered throughout the Congress. So today, this is the most playful session because it's the one that we can all enjoy. We'll be looking at prototypes that work, and they work over and beyond the drawing board. So it's practice after theory. On the first year, we had a group of robots playing football. Then we had the Maggie robot, and on this occasion we will have several more, 4 to be concrete. Let's start with Zaragoza University with Javier Mínguez. He's professor of informatics and system engineering at the University of Zaragoza. And he'll be dealing with something which is to guide a wheelchair with brain waves. It sounds very futuristic, but I'm sure it's going to be around the corner. Thank you very much for your introduction, and thanks to the organizers for allowing us to share with you these technologies. We've developed these technologies in the last few years. We are talking about a wheelchair which is controlled by brain waves, brain activity, and this is a telepresence device which we shall be demonstrating now. This is the wheelchair, and this is a prototype of a technology which tries to reach telepresence for people with a lot of neuromuscular disabilities, people who cannot move about their physical environment. This is an entity which can be hooked up to a family unit or whatever. But let's begin with this demo. This is a robot. You cannot see this, but there is a laser beam and also a video camera. So what is done is to take the video. We should see this on the screen. And this is sent through the internet to the user. So Carlos is the person who's been working on this technology, has an electroencephalogram system over his head. This is what is used in many hospitals. It simply picks up brain activity. This is then digitalized. This is an amplifier back to the computer. We've worked on signal processing, and we can infer the command that the person is thinking of. This is then sent through the internet, and the robot executes it. There is a Wi-Fi going from here to here. Last week we tested this in Japan, and our team were in Osaka, and the robot was in the University of Zaragoza, and we did some navigation and exploration tasks. So this is what you see on your right is the screen that Carlos is seeing right now. He's now booting the system, but before we begin, I'd like to, once the signal is stable, and there's a point that changes everything. What you see right now is the EEG of Carlos. Carlos, could you please make a winking node? Would you blink with your eyes? Blinking movements. Blinking again. Again, please. So as you see, when there's a blinking, this is an artifact, and this has 2 effects. One is to make the problem very difficult from the signal processing point of view. And you see what happens with muscle activity. What we are measuring is the electrooculogram, namely the muscles of blinking. Could you please chew now, masticate? Please chew. One cannot see this very well. Chew again, please. As you may see, there are several clear patterns. This is the activity which is shown by these muscular activities. But since the sensors are very powerful, other signals are picked up. The problem from the muscular point of view is easier than the neurological aspects. So we'll be looking only at the neurological system. So we filter off the artifacts and we collect only the neuronal information. Let's begin, Carlos. This is the screen that Carlos sees right now. The screen is split into two. On the upper part, there are areas of space where he will concentrate to take the robot to it. And in the lower screen, there are some special functions. I assume he will concentrate in some of the areas in the upper panel, in the left upper panel, and within our protocol of action, we will try to validate this. So automatically, the system will recognize the commands and the robot will execute it. In this technology, the robot has autonomous navigation systems inside. So once the command is received, the trajectories are planned, protects the robot from collisions. In this case, it's very simple. And if the robot is going to make some mishap, you can stop it. Okay? So somehow, this is why we need this blue device on top of the robot, which is a telemetric laser, which measures distance to obstacles and avoids them. I'm sorry you cannot see how the video is updated. You see this in real time now, how the robot is sending videos. We can do the demo outside. The robot is sending live video to the user. In turn, there is a special option in the center of the screen. And this is in the center of the screen with two options. Turn right, turn left, and refresh video. And another issue in this technology is that we have this red thing on top of the image, which is a 3D reconstruction done by the robot. The robot with the laser creates a 3D representation of the environment. Since all the sensors are balanced, we can project them on the video that the user is watching here in Barcelona, so that the person need not know the environment where the robot is moving about, and we need to help him interpret the environment the robot is moving in. So Carlos has turned the robot toward the left. I'm sorry you cannot see this. So this type of 3D reconstruction does precisely this. The user can choose areas which are beyond reach. There's a black curtain, and one doesn't see exactly what's behind the curtain. Of course, we are here and we know what there is behind the curtain, but in other circumstances it would not be so easy. Could you change to the exploration mode, please? Now, you cannot see this very well, unfortunately, but the neuronal process we are following is a protocol of P300. It works in the following fashion. The user is now concentrating on some options, either above or below. And then there is a sort of visual stimulation so that the option the person concentrates on is stimulated. There's a neurophysiological phenomenon which we can detect in the EEG thanks to the signal processing activity. Right now we are in exploration mode. Now, the system ought to change, and instead of controlling the navigation system of the robot, we'll be looking at the exploration mode. This allows the robot to explore a certain environment. It is a navigation and exploration system which allows us to move about in any place. So that at the end of the week or next week, we can send the live video, i.e. sending the video to the station where the robot is being controlled. And the next steps will be to send alarms so that the robot can send alarms. For instance, I need help or I need some sort of assistance. And I hope that with this information, we bring to a close this demonstration, this demo. Is that it? Right. I think it's clear. What he's doing now is to align the camera with different points, and this is being explored. And simply to conclude, just before we reached this venue, we calibrated the brain activity. The problem of neural activity is quite difficult for many reasons. One of them is that our brain activity is non-stationary. This means that our activity is very different from each other. All the events in the cortex are different for each one of us. It changes with time. We are now crossing our fingers for Carlos not to become nervous, because if he does, brain activity will change and the machine will have to be adapted. And it changes with time. When he becomes